Hello everyone, welcome back. In this video we're going to take a deeper dive into the conversation of rates of change. So up to this point we've been discussing rates of change and we've been motivating the conversation with a couple ideas. The first was finding a rate of change of, let's say, position over time, which we called velocity. Now when we talked about velocity in the past, right, so we talked about a rate of change. And again, our example as we first explored in this chapter, if y equals, let's say f of t was a height or position function, then the derivative, dy over dt, we called the velocity. Now remember that the units for this is always the units of y over the units of x, if you will. So in this particular case, the units of y would be some height, maybe feet, meters, miles, whatever the case would be, and the unit of time would typically be, seconds, minutes, hours, whatever the case may be. And so we had feet per second in this case. We called that a velocity. And then we also came back after we motivated this conversation and we talked about, slope of a tangent line. So if we had some graph f of x, that delta y over delta x was an average rate of change. It was an average rate of change. I'm going to get lazy here, say ROC. And then when we let the delta x go to 0, we talked about the slope of the tangent line, and that was an instantaneous rate of change. All right, so again, in this video, what we're going to do is we're going to take this conversation a little deeper. So instead of focusing purely on a height position function and its derivative being a velocity, now that we have the tools or the shortcuts of calculating derivatives, or the power rule, quotient rule, product rule, chain rule, what we're going to do again is take a deeper dive and we're going to look at other realms of applications. We're going to look at biology. We'll revisit the physics idea. We're going to look at chemistry. We're going to look at a couple other applications in different fields of science. As a first example, let's revisit the idea or the application of velocity. So in this example, we have the position of a particle moving in the plane is given by s of t equals t cubed minus 6t squared plus 9t. It's supposed to be a t, where t is measured in seconds and s in meters. So let's do a couple different parts here. Let's say part A, what we want to do is find the velocity at time t. So we want to do this in an arbitrary manner. So again, what we know up to this point is that the derivative of s with respect to t, whether we use the prime notation or the Leibniz notation, right, this is our velocity. So we have the shortcut of the power rule at this point. So we're going to say 3t squared minus 12t plus 9 is our velocity function. Now again, this describes the velocity of the particle for any time t. Let's say what we want to do now, part B, let's find the velocity at, let's say, t equals 2 seconds. So, right, once we have our position function, right, our velocity at 2 seconds, so we have our position function, we have its derivative, which is our velocity. We're going to plug 2 into this equation and then crunch that number. And that turns out to be -3. And again, our units are rates of change of y over x. Now recall, as we've discussed before, a velocity is really a vector. It gives, the speed is 3 meters per second. The negative gives a direction. So in a moment, we're going to graph this equation. We're going to, see what that direction means. But if we're traveling in a positive direction, then the negative means I've reversed my direction and I'm traveling in the backwards direction of where we initially started traveling. And let's suppose in part C we want to find when is the particle at rest. Right, so the particle is at rest when its velocity is 0, right, when it has no velocity. Right, so we're going to ask, at what time is the velocity 0? So in regards to our velocity equation, right, we're setting 3t squared minus 12t plus 9 equal to 0. Right, and whenever we're solving a quadratic equation, the simplest thing to do is to look for factoring. If it doesn't factor, we may need to use the quadratic formula. I believe in this case, this equation will factor. I'm going to take out the common factor of 3, and then it looks like this will factor t minus 3, t minus 1. Obviously 3 will never equal 0, so that factor doesn't contribute anything. And then we set the other two factors equal to 0. So we're going to get t equals 3 seconds and t equals 1 second where the particle is at rest. Let's say in part D, we want to ask, when is the particle moving in a positive direction? When is the particle moving in a positive direction and in a negative direction? Now, remember that a couple minutes ago, we had a velocity that was negative. So we know that at some point, in particular at 2 seconds, that was part A, it's moving in a negative direction. But in particular, more specifically, what intervals of time is it moving in a positive direction? Is it moving in a negative direction? So it's going to be moving in a positive direction when v is positive, right? And it's going to be moving in a negative direction when v is negative. So we're really asking, when are these things true? So if I think of my factored form of my derivative, right, where is that positive and where is that negative? Now, a couple different ways that we can handle this. One thing we could do is kind of build a line test, I like to call this. So here's where the particle is at rest. Of course, it starts at 0. Here's when it's at rest. So I'm going to plug in, let's say, t equals 1/2. So if I plug t equals 1/2 into the first factor, well, what is that? If I plug t equals 1/2 into the first factor, I meant to pick my highlighter there, right? 1/2 minus 3 is going to be negative, so I'm going to have a negative number. And when I plug t equals 1/2 into t minus 1, I'm going to get I'm going to get a negative number as well. 1/2 minus 1 would be negative 1/2. So I get a negative times a negative, and I didn't mean for that to be the number 1. I meant to use the pound sign, right? Negative number times negative number is going to give me a positive number. So my derivative is going to be positive here, which means I'm moving in the positive direction. Let's suppose I pick t equals 2 and plug it into my derivative. So 2 minus 3 is going to be negative 1. So I'm going to have a negative. And then 2 minus 1 is positive, right? So again, I'm plugging into each of these factors. That's going to give me a negative number. So it's going to be moving in the negative direction there. And then greater than 3. So I'm going to have, let's pick 4. So if I plug 4 in, 4 minus 3 is positive 1. 4 minus 1 is a positive. So I'm going to get a positive number there. So at t equals 1, at t equals 3, we're at rest. So we're moving in a positive direction. Moving in a positive direction for the intervals t less than 1 and t greater than 3. And then obviously we're moving in a negative direction. I'm just going to say ditto, ditto, ditto when t is between 1 and 3. So what I want to do at this point is let's take out some technology. Let's graph this position equation just to kind of see all this information that we're finding, right, in a visual graphical manner. When I bring up my TI, here's how I'm going to approach this problem. What I'm going to do is I'm going to change to parametric mode, and this is just going to allow me to see a little better the direction that we're traveling. So when I hit the y equals key at this point, what I'm going to do is plug in the position equation that we had, and let's see, that was t cubed minus 6t squared and then plus 9t. Now, one thing I can do, I'm going to let, say, y equals 2. I'm going to explain to you why I do that in a second. So with my set of parametric equations here, when I graph, I see here's my particle traveling in the plane. And if I hit trace, what we're going to notice from 0 to 1 seconds, the particle's moving in the positive direction. Then at 1 second, it changes direction and starts traveling backwards. And then at 3 seconds, it starts moving in the positive direction again. So this is kind of a unique way in which I can kind of visualize that path of travel. And another way to do this, which personally I like a little bit better, I'm going to make y equals t. And the reason that I do that now is it kind of separates the curve and it's not all lying on top of each other. So when I start to trace, I can see, I'm moving in a positive direction, then I'm moving back in a negative direction, and then I'm moving back in a positive direction. So just two different ways to visualize where that's happening. And keep in mind, I could just punch 1 and jump right to t equals 1. I can see there's me changing direction, right, when our velocity was 0. And if I punch in 3, I can see that's where I'm changing direction again, right? T equals 3 was another place where we found the velocity to be 0. All right, let's take a look at another piece of this. Let's say part E, we want to find the total distance traveled. Find the total distance traveled during the first 5 seconds. All right, now we already know that. What we really have to do is we have to find the distance from, 0 to 1. That's going to be the distance in the positive direction. Then we need to find the distance between 1 and 3. And then we need to find the distance from 3 to 5. Now the way we typically would do this, right, distance would be kind of final position minus initial position. So I would really be looking at like s at 1 minus s at 0. And even though this is going to be positive, I'm just going to go ahead and use absolute value to just emphasize, right, we're looking for a distance, we're looking for a positive quantity. And then we're going to have s at 3 minus s at 1. So again, final minus initial. And then we're going to look at s at 5 minus s at 3. If I plug all of that into my calculator, I'm going to get 4 meters plus 4 meters plus 20 meters for each of those intervals, and that's going to be 28 meters total that we travel over the first 5 seconds. All right, let's say part F, we want to find the acceleration. Find the acceleration at, let's say, t equals 4 seconds. Again, we've talked in the past that acceleration is the rate of change of velocity. It's supposed to be a v, right? And which is really the second derivative of position. So we already have our velocity equation, right? That was 3t squared minus 12t plus 9. So what we want to do is take the derivative of the velocity. So we're going to end up with 6t minus 12. So if we want the acceleration at 4 seconds, we're going to plug 4 into that equation. And I'm going to get 12, and then our acceleration will be meters per second squared. One last question here. Let's say we want to know when is the particle speeding up or slowing down? When is the particle speeding up and slowing down? All right, one way to think about this is the following. So we're going to be speeding up. Particle is going to be speeding up when both the velocity and the acceleration have the same sign. So in other words, v is positive and a is positive. So that means, so v, right, my speed is increasing and my acceleration is pushing it in the same direction. Or if v is decreasing and a is negative, again, I'm being pushed in the negative direction. So I'm speeding up. When they're opposite in signs, I'm slowing down. Now, if we think graphically for a moment, right, what did these two equations look like? So we know that the velocity was, what was that? 6t squared minus 12t plus 9. And we had found the velocity was 0 at 1 second and at 3 seconds. So I know, and we had determined that between 1 and 3, the velocity was negative. All right, now our acceleration was 6t minus 12. So if I set acceleration equal to 0, that was at t equals 2. So here's that line, 6t minus 12, roughly. So when are these going to have the same sign? So I can see that velocity is positive from 0 to 1. Acceleration is negative. So we're going to be slowing down from 0 to 1. Now we can see from, I'm going to pick a different color here, we can see from 1 to 2 the velocity is now negative and the acceleration is negative, so they have the same sign there. So from 1 to 2 we're going to be speeding up. The particle is speeding up there. I'm going to change color one more time. From 2 to 3, the velocity is negative, but from 2 to 3, the acceleration is positive. So because they have a different sign, and I had a little typo here, that was from 1 to 2. So from 2 to 3, we're slowing down again. Velocity and acceleration have opposite sign. And then finally, I'm going to go back to a black color. From 3 to infinity, acceleration and velocity are both positive. They have the same sign, and then we are speeding up. So let's take a look at a different example which isn't a position, velocity, acceleration example. So let's suppose that we have a metal rod that has been constructed for us, and let's suppose this entire rod is made of pure steel, let's say. So if the entire rod is made purely of steel, what we call that is homogeneous. So there's no change within the metals or the makeup of the rod. So if we want to find what we call the density, the linear density is defined as being the mass per unit length. So it's common to use the Greek lowercase letter rho. That's what I tried to draw there, the Greek lowercase letter rho. So the mass is measured in kilograms and the distance in meters. The linear density would be a measurement of kilograms per meter. Now, if the makeup of the rod, right, is not homogeneous, let's envision the idea that maybe on the left-hand side we have aluminum, right? And then on the right-hand side we have steel, pure steel, and it's mixed from left to right. So let's say we start with pure aluminum and then we start to mix in some steel, so it gets heavier and heavier. We're getting more and more steel, and then we end up with pure steel at the end. So in this case, the density is changing per position within that rod. So how we would typically measure, right, is just like we did initially with velocity. We would estimate. So if I was finding, let's say, the difference between densities from one position to the next, we could say that whatever that length is, we have, so let's suppose that my mass, right? My mass is described as a function of x. Then my average density over that interval, my average density over that interval is going to be the rate of change of mass from x1 to x2 over the length over that interval, right? x2 minus x1. Now obviously if I let delta x go to 0, then we are looking at, let's say, the instantaneous rate of change. So we're looking at the linear density at one particular value. So very similar, right, analogous to what we did with velocity, rate of change of position over time. We're looking at linear density at any particular position in that rod that is not homogeneous. And again, we're going to use the Greek lowercase letter rho to represent that idea. So if my density is homogeneous, then my rho is a constant. And then if my mass varies as a function of the position x, then my linear density rho will also be a function of where I'm at, right? And where my location is x in that rod. Just to put some equations and numbers to this, right? Let's suppose that the let's suppose the mass of the rod is described by the root function. So if we think graphically for a moment, right, our linear density increases, my mass increases per position x on the rod. Now let's suppose we want to find what is the average distance? I cannot speak today. Find the average density of the rod, let's say from 1 to 2 meters. So again, for average, right, my rho, average density, is going to be the mass at 2 minus the mass at 1 over 2 minus 1, and that's going to give my average. So in this case, my mass was the root function, and I'm going to plug that into my calculator. And since I'm getting a decimal value, let me use the approximation symbol. So I'm getting about 0.41, and I have kilograms per meter. Now let's suppose we take the derivative, and we're going to find, let's find the density right at x equals 1 meters. So that's our derivative, since we're finding the quote-unquote instantaneous density right at 1. That's why it's instantaneous. So my rho in this case is the rate of change of mass per unit length. So when I'm differentiating the root function, I'm going to come back up here. Remember, we're really looking at x to the 1/2. So I'm going to have 1/2 x to the negative 1/2. Right, that's really 1 over 2 root x. So rho at 1 meter is going to be 1 over 2 root 1. So we have 1/2 kilograms per meter as the linear density right at 1 meter. All right, let's take a look at a different example involving derivatives. So a current exists when a charge flows through a wire, or whatever the case may be, right? So if I kind of think of a thick wire, let me see if I can draw a cylinder here. So we have little charges in our wire, and they're flowing in a particular direction. Now what we want to envision, let me take like a cross section, if you will. Let's suppose this is a film here, and this particular slice of film, we have charges flowing through that film. So typically we represent a charge as using the letter Q. So our charge at any particular time we would represent as Q of t. So the average current would be given by the rate of change of charge per unit time. So how much charge is flowing through some unit time. So our instantaneous current, if you will, is going to be described as the derivative of the charge per unit time, and right, and this being instantaneous, if you will. And we usually denote this with the letter I. Some books will use lowercase I, some will use uppercase I. We measure charge, the units of Q is coulombs, and obviously time would be seconds here. And what we typically think of in this case, right, so dq dt has units of coulombs per second, and we call that amperes, or what you typically would hear of as amps.
So let's take a look at an example here. I paused the video so you didn't have to watch me write this problem down. So this example says the quantity of charge that is passed through a point in a wire up to time t is given by this equation, t cubed minus 4t squared plus 7t plus 1. Just do a couple questions here. Let's first say we just want to find, let's ask, what is the current at, let's say, 1 second. So as we just discussed, right, the current as a function of time is going to be the rate of change of charge. So if we take the derivative of q, we're going to get 3t squared minus 8t plus 7. So if we want the current at 1 second, we're plugging 1 into our rate of change of charge. What are we going to get in that case? 3 minus 8 plus 7, so that's negative 5 plus 7, or 2. Remember, this is coulombs per second, but we're going to call that amps. All right, part B, let's say we want to find when is the current at its least. Part B, let's take a look at the question where we want to find the time that the current is the lowest. Now, if we think visually for a moment, when we're looking for the minimum of a function, we're looking for where the derivative is 0, right? We're looking for the slope of the tangent to be 0. Now, what we're wanting to do is minimize the current, which is I. So if this is the graph of I of t, we want to find its minimum. So we need to find where does I prime equal 0, and that's going to give us possible maximum or minimum values. So if I look back up here at I of t is 3t squared minus 8t plus 7. So if I take the derivative, that's going to be 6t minus 8, and we're going to set that equal to 0. So I have 6t equals 8, or t would be 8/6, which is 4/3. So we think that we have found a minimum at 4/3, but we want to make sure we're absolutely sure that that is the case. And what I mean by that is we could have a situation where our derivative is 0 at a maximum, and we just want to double check, right, that we have a minimum in this case. Now again, if we look visually, right, we're going to decrease into a minimum and then increase out. Vice versa, we would increase into a max and decrease out. So what I need is I need I prime to be negative so that I'm decreasing into my minimum value, right? And then I need I prime to be positive so that I'm increasing out of my minimum. So this should be pretty easy to check. If I think of 4/3, right, if I plug 4/3 into I prime, it's going to equal 0. Right? Now, if I jump to the left, let's pick, let's say, 3/3, or the number 1. If I plug 1 into I prime, I'm going to get 6 times 1 minus 8, which obviously is going to be negative 2. So I know my function is decreasing on that interval. And I just want to double check, that I'm increasing out here. So let's double check that. I'm going to plug 2 into I prime. So I'm going to have 6 times 2 minus 8. 12 minus 8 is 4. So I am getting a positive derivative and increasing. So we have verified that at 4/3, current has a minimum value. So we'll just write out in a sentence, current obtains a minimum at t equals 4/3 seconds. Let's take a look at another example. Again, I paused the video real quick so you didn't have to watch me write this out. In this example, a stone is dropped into a lake, creating a circular ripple that travels outward at 70 meters per second. Find the rate at which the area is increasing after 1 second, 3 seconds, and 6 seconds. Now, if we stop for a second and look at what's being asked, we're being asked to find the rate at which the area is increasing in regards to time. Now, if we think of a circle, right, we're being told a stone is dropped, creating a circular ripple. If we think of the area of a circle, we know the formula for area of a circle is pi r squared. So technically, I'm going to use function notation here. I'm going to say a of r equals pi r squared. How am I going to find dA dt? That's what I'm looking for. I'm looking for the rate at which area increases per unit time. I can't take the derivative of a as it sits because a is a function of r, right? I'm going to get dA dr here, which is not what I want. I don't want dA dr. So we got to figure out a way, right? How do we write area as a function of time? That's what we need. What is that equation going to be? Well, I'm given the information in here that the ripple travels outward at 70 centimeters per second. Now, if we think of a circle, let's say, and if we're looking at centimeters per second, that must be the rate at which my radius grows. Now, I don't know why I wrote 70 there, but if we think for a moment, let me draw a circle, right? After 1 second, my radius is 70. After 2 seconds, it's grown to 140 because 70 centimeters every second. And then after 3 seconds, it's grown another 70 centimeters. So we know that the radius is increasing 70 centimeters for every second. So every second of increase, we get 70 more centimeters added onto our radius. So we're able to really do a substitution here, right? If we have the area as a function of radius being pi r squared, and then we have the radius as a function of time being 70t, then one approach here is to just go ahead and substitute and do a composition. So my area as a function of time is going to be pi times 70t squared. Now I'll go ahead and simplify that expression and get 4900 pi times t squared. So now that we have area as a function of time, now we can find dA dt. So what is the derivative of a with respect to time? So I'm just going to pull the constant out, take the derivative of t squared to get 2t, and then I get 9800 pi times t as my derivative. Now the problem asked me for the rate at which area was growing or changing after 1 second, 3 seconds, and 6 seconds. So now I'm just going to find a prime at 1, a prime at 3, and a prime at 6. And the first one, if I plug 1 in, right, I'm obviously going to get 9800 pi. And if we think about area is square centimeters over time. So my units of my derivative here are squared centimeters per second. That's the rate of change of area per unit time. If I plug in 3 seconds and 6 seconds, I'm going to get 29,400 square centimeters per second at 3 seconds. And then at 6 seconds, I get the 58,800 pi square centimeters per second. Remember, these are instantaneous rates of change, right? So right at 1 second, right at 3 seconds, and 6 seconds, those are the rates at which area changes per unit time. Let's take a look at one more example. In this example, we have a tank that holds 5,500 gallons of water, which the water drains from the bottom of the tank in 50 minutes. Torricelli's law gives the volume of water remaining in the tank after t minutes as 5,500 times the quantity 1 minus t over 50 squared. Part A, let's do a couple parts here. Part A, let's find the rate at which the water is draining at t minutes. And again, just like in our prior problem, the rate at which it's draining is the rate at which the volume changes per unit time. So what we're looking for here is, what's dv dt at t equals 10 minutes. So to find dv dt, one thing I could do, and I'm not going to, I could take this binomial and square it and avoid the chain rule. But I'm not going to do that. I'm going to go ahead and use the chain rule here and take the derivative as this sits. So what is v prime at t? So I'm going to take the constant out front. Then I'm going to look at the derivative of the quantity squared. So take the derivative of the outer. It's going to give me 2. I need my pen, not my highlighter. I'm going to have 2 times 1 minus 1 over 50t, all raised to the first. And then I multiply the derivative of the inside. The derivative of 1 is 0. The derivative of a linear function, right, 1 over 50 times t, is just going to be the negative 1 over 50. So now for part A's answer, I'm going to plug 10 into this equation and get negative 176. So first of all, the reason that it's negative is because the tank is draining, right? So my volume is decreasing. So because my volume is getting smaller, my rate of change of volume is negative. And in this case, we have our units being gallons, right? So gallons is my volume, and that's changing per minute, right? So we're going to say negative 176 gallons per minute as my rate of change of volume. Let's suppose letter B says, when is the tank draining the fastest and when is it draining the slowest? Now, when I think about this for a second, I'm looking for where V prime is the largest and V prime is the smallest, and this is a pretty straightforward question, and here's what I mean by that. If we look at V prime is really just the equation of a line. If I take my 5,500 times 2, 1 minus 1 over 50, t to the first, times negative 1 over 50, and I simplify that expression, negative 220 plus 4.4t. And I'm looking for the minimum and the maximum, right? When is the rate of change the largest, when it's the smallest? Now, if I think of sketching this line, real rough sketch, I have a y-intercept of negative 220. And then the line is going to increase, and it's going to increase all the way up to t equals 50, because that's when the tank will stop draining, right? So we know at 50 minutes, the tank is empty, right? The rate of change is 0 when the tank is empty. So we can see the tank is going to be draining the largest at 0 seconds. It's going to be draining at 220 gallons per minute. So it's fastest at t equals 0 seconds, and the rate there is going to be negative 220 gallons per minute. And then we can see at 50 minutes is when it's the slowest, right at 50 minutes. Why did I write seconds up there? Let me fix that. So at t equals 0 minutes, I think I've said seconds a couple times here. I apologize. These are all minutes, right? So fastest at 0 minutes, and then the slowest at t equals 50 minutes, because v at 50 will be 0 gallons per minute. Right, in summary, the whole point of this section was for us to take a look at different types of rates of change, right? Different applications of a derivative. We've been focusing on particular velocity, right? Rate of change of position or rate of change of height over time. And the point of this conversation, again, was take a look at some different ideas. So I'm just pulling up the e-text in Stewart's textbook. It has this great little summary. It says velocity, density, current, power, temperature gradient in physics, rate of reaction, compressibility in chemistry, rate of growth and blood velocity gradients, marginal cost, marginal profit in economics, rate of heat flow, and so on and so on and so forth. All of these examples in this section, right, are a great illustration of the fact that the power of mathematics lies in its abstractness, right? A single concept, such as a derivative, a rate of change, has many different interpretations in each of these sciences. So when we develop the properties of this one mathematical concept, it applies to many different areas. It's much more efficient than developing properties of special concepts in each separate science. Right? So that is really the beauty of mathematics, right? It is the universal language. And there are many other applications of derivatives, rates of change, other than what we're looking at in this section. And as you go deeper into your calculus, your differential equations, your engineering career, you will see other applications and their relevance to your field of study. All right, I look forward to seeing you in the next video.